and then I'll get with you guys in just a second. Alrighty, guys. So let's get into it. So when we get back from break, what we're going to be doing is we're going to be doing our lab for this unit, and it's going to be on this concept right here, calorimetry. And so usually on the AP test, this comes up as an FRQ, and it's because there is a lot of math and conceptualizing on it. So I do want to give you guys a heads up about that. That even if it's not on the test, our lab is going to be on this concept. Okay. All right, so calorimetry, it's basically a measurement for heat flow. So like how energy moves from a hot body to a cold body, okay? And we measure that heat flow using something called a calorimeter, okay? And so this part right here is something that we all know. The more heat you put into an object, the hotter it gets, right? And so different substances, they change temperature when they're heated, but they change a different amount, okay? So for example, a piece of metal would heat up a lot faster than like, I don't know, a pot of water, right? So the temperature changes at a different rate depending on what substance it is, okay? And that the amount that they change, it depends on something called heat capacity, okay? And we use the symbol C to describe it. So heat capacity is the amount of heat that you need to raise its temperature by 1 Kelvin or 1 degree Celsius, okay? So basically, how much energy does it take to increase the temperature of something by 1 degree Celsius, okay? Okay, and every compound, it has a different heat capacity. Okay, the bigger the heat capacity, the more energy it takes to raise the temperature of that object. So let's say I had like a piece of metal. A metal might have a low heat capacity. So it might only take like 0.5 joules to raise the temperature by 1 degree Kelvin, okay? But something like water requires a lot of energy, okay? That's why it takes forever to boil your water. Okay? And it's because it requires 4.18 joules to raise the temperature by 1 degree Kelvin, okay? So the metal, it heats up faster because it has a lower specific heat capacity, okay? Make sense? So depending on what the compound is, and even within metals, there's they all have a different heat capacity. So some metals heat up faster than other metals, and so that's what heat capacity is. Okay, now there's two types of heat capacity we'll be talking about. The first is Cm, that's the heat capacity of 1 mole. And then there's specific heat capacity. This is the one that we're gonna focus on mostly as Cs, and it's the heat capacity of 1 gram of a substance. So how much energy does it take to increase 1 gram of something by 1 degree Kelvin? And this is the formula right here. Okay, so we're going to jump into an example in just a second, but let me just explain how to use the formula before we do that. Okay. So like we said, Cs, that's the heat capacity. It's going to equal the amount of heat that is transferred divided by the mass of the substance, and delta is change, so the change in temperature. Okay, so we're going to use this formula to answer this problem. So it says it takes 209 joules to increase the temperature of 50 grams of water by 1 Kelvin. Okay, we're going to calculate the specific heat of water. Okay, so if you guys feel like you guys can do this on your own, it's kind of just a plug and chug equation. You guys can try it, but I'm going to take it step by step since this might still be a little bit confusing. Okay, I'll pull up my calculator here. So we just need to plug in the values into the correct variable right here. So let's start with the one that we're looking for. Which of these variables are we solving for? Yeah, CS, right? It's asking calculate the specific heat of water. And then we said specific heat is CS. So we're going to be looking for CS, which means we need to plug in Q, M, and delta T. Okay, so we're solving for CS. Okay, say 209 joules. Okay, so if it's in joules, is it heat, mass, or temperature? Yeah, heat. Joules is always going to represent heat. So that's going to be 209. Okay, we're going to divide that by 50 grams. This one's easy. It's mass. So we'll put 50 grams on the bottom. And if we're raising the temperature of water by 1 Kelvin, it's going to be positive 1. So it'll be 1K. Okay, so there you go. We can solve now how much energy it takes to raise the temperature of water by, or 50 gram, to raise the temperature of 50 grams of water by 1 degree Kelvin. Okay, so let's calculate the CS. We would do 209, and then we would divide that by 50, and then we get 4.18. So what this tells us is the specific heat of water is 4.18 joules per gram Kelvin. Okay, so the units for specific heat is going to be joules divided by grams times Kelvin. Okay, so the way that we would read this unit of measurement is it takes 4.18 joules to raise 1 gram of water by 1 Kelvin. Okay. And so every different substance is going to have a different specific heat, but that's how you would calculate for it. This is how we actually do it in lab. We just weigh what we're trying to find the specific heat of. We heat it up. We see how much the temperature changes, and then that lets us find the specific heat. Okay. All right, any questions about using that formula? Okay, let's move on to the next part. So here we have a table, and it tells you the specific heat of some substances, some different chemicals. Okay, so nitrogen gas, 1.04, aluminum is 0.9, iron is 0.45, and we just found water, right? We said that water is 4.18. So by looking at this table, which one of these compounds takes the most energy to heat up? Not aluminum, just the whole table.
Oh,
which one? What do you guys think? Yeah, it's going to be water. Water has the highest number for the specific heat. So water takes the most energy to heat up. Okay, so if you want to increase the temperature of water, you have to put a lot of energy into it. Okay, what about the lowest? Which one is the easiest to heat up? Yeah, Hg. This is mercury, liquid mercury. Okay, and so Hg, it's the easiest to heat up because it has the lowest specific heat. Okay, so that's basically how you read the table. These are the values, and these are all CS, so specific heat. These are the specific heat CS values. Okay, now if we know how much energy it takes to heat up something, we can actually figure out how heat moves around, how much energy moves around between two different substances. So what we can do is we can rearrange the specific heat equation like this. Remember, it was a CS is Q over M delta T. We can rearrange it into this. And make sure you guys write this down because this is the form of the equation we'll be using the most often. Okay. So Q equals CS M delta T. Now, the reason why we use this form of the equation the most is because what's the hardest thing to like figure out about heat? It's the actual heat that's moved around, right? You can't like put a thermometer on something and be like, oh, this is moving like 40 joules of heat, right? We can't really figure that out. But the other things in this equation are easy to figure out. Mass, how do we figure out mass? Yeah, you just put it on a scale. The change in temperature, this one you can just put a thermometer on it, right? And you can see how the temperature changes. And then CS, you can just look this up because a bunch of nerds have figured it out already. So those three are easy to figure out. Yeah.
Would we ever have to memorize CS?
No, you're never gonna have to memorize any of them. The only one that you probably will end up memorizing is water, just because you use it so often? Yeah, good question. Okay, so we're going to be using this form of the equation, which means a lot of times in your lab, you're going to be looking for the heat flow. Okay, so this equation allows us to calculate how much heat a substance gains or loses using its specific heat, okay? As long as we measure the mass and the temperature change, which isn't too difficult to do. Okay, so let's try 6.25. See if you guys can use the new equation right here to figure it out. How much heat is needed to warm 1,000 grams of water from 22 degrees Celsius to 98 degrees Celsius? Shoot, why not? So how much heat is needed to warm 1,000 grams of water from 22 degrees Celsius to 98 degrees Celsius? I'll give you guys maybe another minute to finish that up. Yeah, what's up, great? So change in temperature, you can use Celsius as long as it's talking about change. So you don't need to convert it to Kelvin. Yeah, because change is going to be the same, whether you're going from 100 Kelvin or 100 degrees Celsius, the difference doesn't change. Yeah. Yeah. Because they're both absolutes. Alrighty, guys, so let's go over this one. Let's just plug in the values. So we have our equation right here, Q equals CS M delta T. So it's asking us to find how much heat, so which means we're looking for Q. We're looking for the heat flow. Okay, and we're trying to heat up water, 1,000 grams of water. So let's plug that in. So Q. Now let's start with CS. If it's water, what's the specific heat of water? Yeah, 4.18, and we said the units are joules, grams, and then it can be either Kelvin or degrees Celsius. Okay, gonna multiply that by the mass, which is 1,000 grams, and then the delta T is the change in temperature, so that would be 98 degrees Celsius minus 22 degrees Celsius. Okay, so if we are talking about change in temperature, you do not need to convert from Celsius to Kelvin. However, if we are talking about just regular temperature, if we're talking about the temperature of the object, then you do need to change into Kelvin, okay? So delta T, you don't need to change. Temperature, you do need to change, okay? So just keep that in mind. All right, so let's do a little plug and chug. So let's start with the back end. So we got our change in temperature, which is going to be 76. Going to multiply that by the specific heat, 4.18. Going to multiply that by 1,000. And then there you go. That is going to be your answer, 317,680. And if we want to figure out the units, the joules cancel out, the Celsius will cancel out with each other. And so the answer will be in joules. Okay. So 1 gram of water is 1 liter of water, okay? All right, so let's actually do something fun. let's figure out how many calories it takes to heat up this water. Okay.
You understand that his idea of fun and everyone else's idea of fun obviously is different.
Obviously.
Let's do something fun, kids.
Let's do something fun.
Calculate.
That's not fun, dude, because then I see how much the government is stealing from me. All right, so so the calories in our food, okay, 1 joule is equal to 0.0000239 calories. So I want you guys to figure out how many calories it takes in order to do this heating up, okay, to heat up 1,000 grams of water from 22 degrees Celsius to 98 degrees Celsius. So basically bringing it from room temperature up to boiling. And so here we can figure out how much we actually eat, how much energy that is. I know, fun, right? It's a lot of energy, right? Okay, so hopefully you're able to see that it's just a simple dimensional analysis calculation. So we're going to put joules on top. This is our conversion unit. So we're going to put 1 joule on the bottom. We're going to put 0.000239 calories on the top. And so we just need to multiply the value that we got by 0.000239. And so it's going to take about 75.926 calories. Okay. So the energy that's in about, I think it's like 3 Oreos. I think it's like 3 Oreos. About 3 Oreos of calorie energy. That's what it takes to bring a water from room temperature up to about boiling. Okay. So that's how much. Yeah, we use a lot of energy. Yeah. Okay. Any questions? Easy peasy. A lot of fun, right, guys? Actually, let me actually look that up. Let's look up calories. Oreo calories. Oh, never mind. Holy cow. Wait, there's no way. Hold up. Show you guys. There is no way 1 Oreo's. 3 Oreos is 160 calories. Holy cow. So we can take 1 Oreo, and the energy in 1 Oreo can heat up water from room temperature to boiling. That's a lot of energy. Goodness. I'm gonna go eat an Oreo at home. Okay, so that's just one way we can look at temperature change. Okay. Now, this right here is what we are going to be doing in our lab. So what I want you guys to do is take about a minute. I want you guys to just copy this diagram. Okay, don't make it perfect. I'll do my picture right here just so you guys know the low standards I have for drawing. Okay, so I'm literally gonna draw a cup. I'm gonna draw my water. I'm gonna draw a thermometer in there. Okay, so something like this is fine. You guys don't need to make it super fancy. Okay, because this is just to understand the concept. So we're actually going to be making a calorimeter in this class, and we are going to be finding the specific heat of different metals. Okay, so for our lab after Thanksgiving break, I'm going to give you a set of 5 different metals like this. And then what you're going to be doing is you're going to be using a calorimeter that you guys make in class in order to figure out what the specific heat of these metals are. So that's going to be coming down the pipeline. We're going to learn the concept before break. We'll review it before the lab, but this is the lab we'll be doing, I believe, December 3rd, so the first week back. Yeah. Huh? I think we're on break November 29th, so. Yes, make sure you guys sign up for the AP test on College Board. I sent out a message, but make sure you're signed up on College Board for this class. All right, so I'll give you guys another minute to copy down that diagram again. Don't make it too fancy. Okay, and what we're gonna do is we're gonna talk about how we use a calorimeter to find energy of a reaction or a substance. Okay. Okay, so well, as you guys finish up the drawings, let me just go over a couple things about this calorimeter. Okay, so basically in a calorimeter, we usually have, you know, we go very high tech here. So we use styrofoam cups and then we put some water inside of it. Okay, so we have water inside a styrofoam cup. Now, we said earlier that we know the specific heat of water, right? Okay, water will always have a specific heat of 4.18 joules grams Kelvin. Okay, so water is a good way for us to figure out the energy that flows from a reaction that comes out of a reaction. So let's say I put a bomb inside of water, okay? Okay, and the bomb blows up. Okay, so this is gonna be an exothermic reaction, right? And it's gonna release energy into the water. So if a bomb blows up inside, let's say a big pool, right? Not a styrofoam cup, like a pool of water. What's gonna happen to the temperature of the water? Yeah, the temperature of the water is gonna go up. Now, if I had a little thermometer stuck in there, right? I can find out how much the temperature of the water changes, right? And if I know the temperature change of the water, if I know the delta T, and if I know how much water is inside of my calorimeter, I can use that to figure out how much energy the water absorbed, right? Because if I have the specific heat, if I know how much water I have, if I know how much the temperature changed, we can figure out how much heat went into the water. Does that make sense? Now, what we can do is we can also use a little bit of reasoning to figure out, hey, the heat that goes in the water, it's the same as the heat that came out of the reaction, right? Because when the bomb blows up, all the energy goes into the water, right? So let's say that if the water absorbed 100 joules of heat, that means that the reaction, the bomb, it gave 100 joules of heat to the water. Does that make sense? It's the same amount. The only difference is for the water, it's positive heat because it absorbs heat, whereas for the bomb or the reaction, it's going to be negative heat. It'll release the heat. Does that make sense? So what we can do is we can use a calorimeter to figure out how much energy a reaction or a bomb or something like that releases when it goes off. Okay, so that's what we'll be doing in our lab. But let's do one example just so that we can see what's going on, okay? Alrighty, so we're gonna do 6.26. Now this is gonna be a pretty big problem. There's a lot of numbers, a lot of words, and so I wanna make sure that we have a good understanding of it. So what we're gonna do first is we're going to draw a picture of the system because as you guys know, I'm a great artist. And so I want to share my talents with you guys and bless all of you, okay? So I'm going to draw who laughed? Okay, so we're going to draw a calorimeter. Okay, this is Mr. O's calorimeter. It kind of looks like a Chinese food takeout box, right? Okay, and then inside our calorimeter, we're going to have some water. And then I'm going to draw a little thermometer in here. So this is going to be my thermometer. So beautiful. It's an incredible drawing. Okay, and then this looks like a piece of poop, but this is going to be my thermometer. Okay, so this is our calorimeter. So draw something similar to this on your paper. We are going to be writing inside of we're going to be writing a little bit. So as long as you have some space in there, you're all good. All right, everyone good to go? Okay. So, in this like lab, suppose that you're mixing 50 milliliters of 2 molar hydrochloric acid and 50 milliliters of 1 molar sodium hydroxide. Okay. The temperature of the solution increases from 21 degrees Celsius to 30 degrees Celsius. Okay, so I'm going to write the delta T. The delta T, the change in temperature of the water is going to be what? Yeah, 9 degrees Celsius. Okay, the temperature is going to change 9 degrees. Now I'm going to write positive just to show that the temperature increased. Okay, so let's stop right there. Okay, so the temperature increased by 9 degrees Celsius. Okay, temperature of the water. So does that mean the reaction was exothermic or endothermic? Who thinks exo? Who thinks that the reaction releases energy? Who thinks it's endo, the reaction absorbs energy? Oh, okay, so let's think about that logically, okay? So the temperature of the water increased, right? Hey, what's up? For me? Oh, what is it?
Like feminine products.
Oh, okay, you can just leave it on the countertop.
Okay.
Are they for me?
Yeah.
Sorry, I could have rephrased that. Yeah, thank you. All right, so thank you, ladies.
Of course.
I'll be sure to make good use of them. Okay, so the temperature of the water increased by 9 degrees Celsius, okay? So if the temperature of the water increased, does that mean the water absorbed heat or released heat? Yeah, the water is gonna absorb heat, right? The water absorbed heat, okay, which means it had a positive Q value. Okay, so if the water absorbed heat, does that mean the reaction released heat or absorbed heat? Yeah, the reaction released heat, right? Okay, because in order for the temperature of the water to go up, that means the reaction has to give energy to the water. So it's negative Q. Okay, and if a reaction releases heat, what kind of reaction is it? Yeah, it's going to be an exothermic reaction. Okay, because the reaction, when you mix HCl and you combine it with NaOH, it's going to give energy to the water, which is why the temperature of the water increased. Okay. So this is kind of like the concept behind, like, if you have like a hand warmer, right? You pop the thing inside the hand warmer and then you shake it and then it heats up, right? It's because the chemicals inside the hand warmer are releasing energy into the hand warmer, which goes to your hand and warms your hand. Okay, the opposite is true for like cold packs. You pop the bubble in the cold pack and it starts getting cold. That would be an endothermic reaction. It's taking energy into the reaction. Okay. Does that make sense? Why it's exo? Okay, so we know the water is going to have a positive Q value and the reaction is going to have a negative Q value. Okay, so it tells us the combined solution has a total volume of 100 milliliters. Okay, so this whole thing right here is going to be 100 milliliters. Okay, and it tells you that the density is 1 gram per milliliter and the specific heat is 4.18 joules gram Kelvin. Okay, so whew, that's a lot of information. Oh, we didn't even talk about the molarity. Okay, the hydrochloric acid is 50 milliliters of 2 molar, and the NaOH is 1 molar, 50 milliliters. Okay. All right. Any questions on like what's going on inside this situation? Does that make sense? Okay, so we're mixing HCl NaOH. It's exothermic, so it gives energy to the water, and the water temperature goes up. Okay. All right, so let's start doing part B now. We're going to calculate the enthalpy change for the reaction, assuming the calorimeter loses negligible amount of heat, which means just use the numbers. You don't have to think about, hey, how much energy is lost. Okay, so we're going to be looking for the enthalpy change. Now, For enthalpy change, it tells us that the units are going to be kilojoule moles of hydrochloric acid, which means that we have to end the problem. We have to have kilojoules per mole of hydrochloric acid. Okay, so all the calculations that we do, they need to take us to this point right here. Okay. Now it's asking us for the reaction, which means that we have to write the balanced chemical equation. Okay, so that means we start off with HCl and we're going to combine that with NaOH. Okay, anyone remember what type of equation this is? Yeah, neutralization. Oh, warms my heart that you guys know that. Okay, so in a neutralization reaction, it's always going to form water and a salt. Okay, so we do just double replacement. So we have the positive and negative of one of them, the positive and negative of the other one, which means that it'll produce NaCl, which is a salt or NaCl. Okay. Any questions on how we set up the equation? Make sense? All right. Now what we're going to do is we're going to use some of the numbers that we have. Well, it tells us that we have 2 molarity HCl and 50 milliliters of it. And then we have 1 molarity of NaOH and we have 50 milliliters of that. Okay, now when we look at a balanced chemical equation, what do we always want to turn our numbers into? What unit of measurement? Not grams. Yeah, moles. We always want to turn it into moles. Okay, so I'm going to give you guys like a minute. I want you guys to figure out how many moles of HCl and how many moles of NaOH we have here. Okay, if you guys don't remember, the molarity formula is moles over liters. Okay, so I want you guys to use the numbers that we have for HCl and NaOH, and I want you guys to calculate how many moles of each we have. Alrighty, I'll give you guys maybe 30 more seconds to convert into moles. How does this man play so much music? Like, alrighty guys, so hopefully you were able to figure out that this is going to be 0.1 moles of HCl and 0.05 moles of NaOH. Okay. Everybody got that? Okay. So now what we can do is we can start calculating for the heat transfer. Now earlier we said that the energy absorbed by the water has to equal the opposite of the energy released by the reaction, right? Okay, because in order for the temperature of the water to go up, the reaction needs to release energy. Okay, so what we're going to do now is we're going to use the information we have about water to figure out information about the reaction, okay? So we know that the heat absorbed by the water, okay, we have to use the specific heat, the mass, and the delta T, okay? So what we can do is we can just start plugging in our values, okay? So let's look at specific heat. What is the specific heat of the solution inside of the calorimeter? Yeah, it tells you right here, 4.18. Okay, so we're going to plug that in. 4.18 joules gram Kelvin. Okay, now let's look at the mass of the solution. Okay. Does it tell us directly what the mass of the solution is? It doesn't, right? We don't have any grams. However, we do have volume, which is 100 milliliters. Okay. And we also have the density. The density is 1 gram per milliliter. So if we have the volume and the density, we can figure out the grams. It's pretty simple, right? Because if something is grams per milliliters, that's the same thing as 1 gram is equal to 1 milliliter. Okay, that's what the density is for. And so what we can do is we can set up a fraction and plug this into the fraction. So we have 1 milliliter, 1 gram, and then the milliliters cancel out, which means that we have 100 grams of solution. Okay, so that means we have 100 grams of solution. Does that make sense? All right, and then lastly, the change in temperature. We said it went from 21 to 30, which means it was a positive 9 degrees Celsius change. Okay, so I'm gonna give you guys a minute. I want you guys to calculate how much energy, how much heat did the water absorb from the reaction? Alrighty, so all you need to do is plug and chug 4.18 times 100 times 9. That gives you 3762. And what's our unit of measurement? Yeah, it's going to be joules. And we know that because grams cancels out. And then change in Kelvin is same as change in Celsius, so they cancel out. And so you get 3762 joules. Okay, so that means the water absorbed 3,762 joules from the reaction, which means how much energy did the reaction release? Yeah, the same thing, but negative, which means that the Q of the reaction, the energy released by the reaction is negative 3762 joules. Okay, so energy was a product in this reaction. This reaction released 3,762 joules. Now we're almost done, but we're not quite done because it's asking us for the kilojoules per moles of HCl. Okay, so we need to convert this into kilojoules. Now we know that it's 1,000 joules per 1 kilojoule. Okay, so we can move the decimal 3 times to the left. That'll give us negative 3.762 kilojoules. Okay, but we're still not done because it's asking us per mole of HCl. So what we're gonna do is we're gonna take that value, negative 3.762 kilojoules, and then we're gonna divide it by the moles of HCl, which is gonna be 0.1 moles. Okay, and that'll give us a final answer of negative 37.62, and the units will be kilojoules per mole of HCl. Okay, and there we go. That is the end of that problem. Okay, so that's basically how a calorimeter works. We basically just put a reaction inside of water. We figure out how much the water temperature increases. And then based on that, we can find out how much energy the reaction releases or absorbs. All right, any questions about that problem? Again, we're gonna spend some time reviewing this after the break because we will be doing our lab on this. The exam? Yeah, you'll have this on the exam. Yeah, what's up? Both. Yeah, you can expect this on the AP too. I think they give it every like other year. Yeah, every other year there's a problem like this. I don't know. It's always a mystery. I'm telling you, dude, this class is unfair. We don't even know what's gonna be on the test specifically. Okay, so let's go on to 6.27. This is another calorimetry problem. Okay. So what I want you guys to do is we're gonna do the calculations together. It's a little different than the one that we just did, but I want you guys to just draw the system. I want you guys to draw what's going on in this calorimeter. Try to make sense of what the problem is asking you to find. Okay. So take about like a minute, minute and a half. You could draw a picture of the system just to see what is going on. And then after that, we'll start solving it together. Okay, and then after that, we will take our break. So take a second to just copy down what's going on. Try to make sense of it. That's okay. Yeah, no, I only need like this. No, that's fine. I'll give you maybe another 20 seconds before I draw it. And then if you guys feel confident trying this out on your own, go ahead and try. It's okay to get it wrong. I mean, that's why we're all learning, right? And as you guys know, I still make mistakes. Half the time, I don't even know what's going on. Alrighty, guys. So let's go over this problem. Okay, so in this calorimetry problem, it's saying that suppose you have a 418 gram unknown metal. Okay, so I have a piece of metal. Okay. All we know about it is that it is 418 grams, and we know that the temperature of the metal is 98 degrees Celsius. Okay, so it's a pretty hot piece of metal, over 200 degrees. Okay, we're gonna put the metal inside the calorimeter. The calorimeter, it tells us that the water in the calorimeter, we have 2,000 milliliters of it. Okay, which means that we have 2,000 grams of it. Okay, because the density is 1 gram per milliliter. So if we have 2,000 milliliters, we have 2,000 grams. It tells us that the water originally was at 30 degrees Celsius. So that's the initial temperature. So TI, temperature initial, is 30 degrees Celsius. Okay, and so we'll stop right there. Okay, so let's just think about this logically. the piece of metal is hotter than the water, right? So if I put a hot piece of metal into water, what's going to happen to the temperature of the water? Yeah, the temperature of the water is going to go up, but what's going to happen to the temperature of the metal? Yeah, the temperature of the metal is going to go down. And what's going to happen? They're going to meet somewhere in the middle, right? And so that's what's happening right here. It's telling us the temperature in the calorimeter comes to equilibrium at 31.5 degrees Celsius, which means that the initial temperature of the metal was 98 degrees, but the final temperature of the water is the same as the final temperature of the water. Okay, because if the metal is in the water, eventually they're going to come to the same temperature, right? The temperature of the metal is going to go down and the temperature of the water is going to go up. Does that make sense? Okay. And so based on that information, the question is asking us, figure out what the metal is. Okay, now this might seem kind of weird and like a random jump in logic, but we can think about it this way in terms of the Q equation, okay? So we know that the heat of the water must equal the opposite of the heat released by the metal, right? Because the water is absorbing energy, right? Because it's getting heated up, but the metal is losing energy because the metal is cooling down. So we can actually write this equation right here. The heat of the water is equal to the opposite of the heat of the metal because it's the same amount of energy. It's just one is absorbing it and one is losing it. And so what we can do is we can expand this equation a little bit. We can write the specific heat of water times the mass and the change in temperature of the water, right? Because that's just what Q is. We know that Q is equal to Cm delta T. Okay, so for water, the specific heat of water, the mass of water, and the temperature change of water is equal to the opposite of the C of the metal, the mass of the metal, and the delta T of the metal. Okay. Does that make sense? Why they're opposites? All we're doing is taking this concept that, hey, the water is going to absorb the same amount of energy that the metal releases, and we're just taking that equation and just blowing it up so that we have more variables to work with. Okay, so let me actually, does anyone still need this picture or does the concept make sense? Okay, just so I have a little bit more room. So again, just to reiterate, the heat that the water absorbs, okay, is equal to the opposite of the heat that the metal releases. And if we want to expand this equation, we can say that the specific heat of water times the mass of water and the temperature change of water is equal to negative the specific heat of the metal, the mass of the metal, and the temperature change of the metal. Okay, so all we're doing is making this equation bigger so that we can plug the numbers in. Now, the question is asking us at the very end to figure out what metal we put inside of the water. Okay, and then here we have a bunch of specific heat. So we have 3 different metals, mercury, iron, and copper, and it tells us the specific heat. So if we can calculate this right here, if we can calculate the specific heat of the metal, we can figure out what metal this is. Okay, and this is actually what people do in real life. If they're trying to figure out what metal or what substance something is, something unknown, they just put in a calorimeter sometimes and you can just calculate what it is. And based on the specific heats that we know, we can figure out what that compound is. So what we're going to be doing is we're going to be calculating for the specific heat of the metal, and that'll let us figure out which metal it is. Okay? Any questions about that? Yes. Well, I mean, they're all being multiplied, so we don't need the parentheses. You could. So either way you write it is totally fine. Okay, good question. Any other questions? Okay, let's start plugging some numbers in. All right, so let's do the specific heat of water. We all know what that is, right? What's the specific heat of water? Yeah, 4.18. And then you don't have to do the 4. So we'll do 4.18. 0.18. Actually, I'll do the 4 this time. Okay, joules, gram, and then degrees Celsius. Okay, that's the specific heat of water. Okay, what's the mass of water that we have? Yeah, we have 2,000 milliliters, which is the same thing as 2,000 grams. And then we have our delta T. Now, for the delta T of water, we know that it's equal to the final temperature minus the initial temperature. Okay, what was the final temperature of the water? Yeah, 31.5 subtracted by the original temperature, which is 30 degrees Celsius. And so our answer will be 1.5, which makes sense because it's a positive number. The temperature goes up. And so we'll have 1.5 degrees Celsius. Okay, so that's going to be the left side. Make sense so far? All right, now we have to do the right side. Now we don't know the specific heat of the metal. That's what we're looking for. Okay, now what we can actually do is we can kind of move everything to the left side by dividing it, right? Because they're all being multiplied, so you can divide by everything here on the other side. So the mass of the metal says it's 418 grams. So the mass of the metal is 418 grams. The temperature change of the metal is going to be the final temperature, right? So the delta T of the metal, the final temperature of the metal is 31.5 minus the original temperature, which is 98 degrees Celsius. Okay, and this answer is going to make sense as well because the temperature went down. So if the temperature goes down, that means we have to have a negative change in temperature. And so if we plug that into the calculator, we'll get 31.5 minus 98. That'll be negative 66.5. Negative 66.5 degrees Celsius. Okay, and so that's going to be our equation. Okay. Everyone good with that? Okay, and if I just wanted to make one thing a little bit easier, I can move the negative sign to the left side so that we can just plug this into a calculator and we can solve out. Okay. All right, let's plug and chug and figure out what the heck this metal is. Okay. So I have 4.18 on the top, 184 on the top, times 2,000 times 1.5. I'm going to divide that by 418. Now I know that the negative here and the negative here are going to cancel out, so it's going to be a positive number, which makes sense because you have to have a positive specific heat. And then we're going to divide that by 66.5. And for our final answer, the specific heat of the metal is going to be 0.45, and I'll round it up to 2 joules, grams, Kelvin. Okay, so if we look at the table, what metal were we working with? Yeah, iron, Fe. Okay, because it's the closest to the specific heat. Okay, and so that is how you can figure out the identity of an unknown substance by using calorimetry. And this is what you're going to be doing in your lab. Again, I'm going to be giving you 5 different pieces of metal for your lab after break. And then you're just going to have to figure out what the identity of those metals are based on the specific heat. Okay. All righty, guys. Any questions about that? Okay, so we'll take a 7-minute break, and after that, we'll come back together and we'll finish up Unit 6. I know that was a lot, and these are long problems, so thanks for sticking through it. So let's take 7 minutes, and then we will come back together. Back. All righty, guys. So let's go on to the last topic for this unit. Now, what I want you guys to do before we start is to draw this kind of diagram. It doesn't need to be ginormous like it is on the screen right here. But we are going to be talking about something called heat of formation and heat of vaporization. Now, you're going to have to use this chart because it's very helpful for kind of envisioning what's going on with this concept. So make sure you guys draw it somewhere on your paper. Somewhat big. You're going to have to do a little writing next to it, but it doesn't need to be like huge. Don't let it like take up half a page or something like that. It's not worth it. Okay, so this is the last concept for Unit 6. Okay, and this question does not show up very often on the AP test, but sometimes it does. And so it's important to know about this. Okay, so let's just talk about something that we already know. Okay, so everybody knows if you give heat to something, it's going to get hotter, right? The temperature is going to go up. So we all know that as you put in more energy, the temperature is going to go up, 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 right? That's kind of the normal line of thinking. And this is just kind of logical. However, this is actually not true. This is not how temperature rises with energy. Okay, it's kind of weird, but when a substance, right? So normally, like if we had water, right, or like a piece of ice, right? If I have ice, if I put energy into it, the temperature is going to go up, right? So this will be my ice. However, there's a point where the ice is going to change into something else, right? What does ice change into if you heat it up? Yeah, it's going to turn into agua, water, right? Now, what's the process we call from going from ice to water, solid to liquid? Yeah, we call that melting, right? So at a certain point, we're going to hit what we call the melting point, right? That's the temperature at which the solid becomes a liquid. Okay, so for water, that's 0 degrees Celsius. Now, when the temperature of the ice hits the melting point, it's actually going to stay there. The temperature will not go up, even though you keep putting energy into the ice. Oh, that's weird, right? You can keep putting energy into the ice, but it won't raise in temperature. Anyone want to take a guess why? Why would the temperature of the ice not go up, even though I'm still pumping energy into it? Okay, so you do need to put in energy to make it move faster, but why would the temperature not go up, right? You're putting energy in. Where's that energy going? It's weird, right? So let's think of it this way. What is temperature? What does temperature measure? Yeah, it's the movement, right? So the movement of the molecules. Okay. So the temperature, basically like how they're vibrating, how they're moving, right? Now, once you get to the melting point, let's talk about solids. How are molecules interacting with each other when they're solid? Not much. They're kind of like stuck together, right? They're pretty set in place. So it's kind of like they're like in line. They're set in place like this for a solid, right? Okay, but what about for a liquid? How do the molecules interact in a liquid? They kind of like, they can move more freely, right? They're not as stuck together. So in a liquid, they kind of like, they're like a little bit loose. They're not completely loose, but they could like, there's room for them to move around, right? Liquids, the molecules can move around in a liquid, whereas in a solid, they're kind of locked into place. They're stuck to specific ones. Now, when you get to the melting point, what has to happen is you need to break up those molecules. So what you're going to be doing is you're going to be putting a bunch of energy into the solid, but the temperature won't go up because the molecules aren't moving faster. Instead, what they're doing is they're separating from one another. Okay, and so that's why the temperature does not change at the melting point, even though you put in more energy. Does that make sense? It's because you're not making them move faster, you're just breaking them apart from one another. Okay, and so what's going to happen is it's going to stay the same temperature until all of the molecules are broken up. And then after that, the temperature can go up as you put in more energy. And we'll call that the water, or that's the liquid phase. Okay. Does that make sense though? It's because temperature is how fast the molecules move. When it's melting, the molecules aren't going to move faster. They're just breaking up with the other molecules that they're stuck to. So that's called the melting point. Now, this part right here on this graph, we call that the heat of formation. Okay, so the energy that it takes to melt a substance, that's called the heat of formation. Okay, now this is important because ice has a specific heat. The specific heat of ice is, let me double check. Oh, the specific heat of ice is 2.09 joules gram Kelvin, which is different from water, right? We know that water has a specific heat of 4.18 joules gram Kelvin. So ice and water, they have a different specific heat. Okay, it takes less energy to heat up ice than it does to heat up water. Okay, but the heat of formation is different from those things as well. It's the energy it takes to break the molecules apart. Okay, and we'll talk about how to use that in just a second. Okay, and then the same thing happens when you get to the boiling point, okay, or the vaporization point. Okay, the temperature of the water will stop increasing, and instead it'll take a lot of energy in order to break up all the water molecules, because we know that in a liquid the molecules are moving, but they're still kind of next to each other. But in the boiling point, what happens? The molecules, when they turn to gas, they just start flying around. So that takes a lot of energy too. So the boiling point is, it's not going to increase in temperature until all of the molecules are broken apart. And we call that the heat, not het, the heat of vaporization. I just say vap. Okay, and this is where we go into steam, or that's going to be the gas phase. And for the specific heat is going to be 1.996 joules gram Kelvin. Okay. So when you're trying to find out how much energy it takes, for example, to go from a piece of ice to steam, what you're going to have to do is you're going to first have to calculate how much energy it takes to melt it. Then you're going to have to find the heat of formation. Then you're going to have to find out how much energy it takes to heat up the water, how much energy it takes to vaporize the water, and then how much energy it takes to increase the temperature of the steam. So there's going to be 5 different parts that you're going to have to do. If I ask you, hey, how much energy does it take to melt ice that's at -10 degrees Celsius and take it to, I don't know, 111 degrees Celsius steam? You're going to have to add 5 different parts in order to find out how much energy it takes, because they're all different. You can't just have one equation, because you're going to have one equation for the specific heat of ice, one equation for the heat of formation, one equation for the heating of water, one equation for vaporization, and then one equation for heating up steam. Okay, so kind of makes the calculations really annoying, but in order to break apart the molecules in the different states of matter, that takes a different amount of energy than just heating them up. Okay. Conceptually, does that make sense? Okay, so it's different from just heating something up, because you have to actually break the molecules once they get to a certain temperature. Okay. All righty, so let's hold up. Okay, let's actually go over a problem, and then I think we'll be done with that. You guys can try 6.29 on your own, but let's do 6.28 together, and then we'll be done for the day, okay? That's ugly. Okay, oh, and one more thing. Just like specific heat, every molecule has their own individual melting points, boiling points, and heat of vaporization and formation. You guys don't need to memorize any of this. The only thing you really need to memorize is the melting point, which, you know, we always know it's 0 degrees Celsius for water, and the boiling point of water. Okay. You don't need to memorize the heat of fusion or vaporization, but just recognize different chemicals, they melt at different temperatures and they boil at different temperatures too. Just know that there's a difference. The only thing you really need to know is water freezes and melts at 0 degrees Celsius and boils or condenses at 100 degrees Celsius. Okay, so let's do this problem right here. 6.28. I want you to calculate the energy it takes to turn 14 grams of water into, of water at certain temperature, right? That's pretty important. At 20 degrees Celsius into 150 degrees steam. Okay, so if you guys feel confident doing this on your own, feel free to do that. But I'm gonna take it step by step, okay? So what I like to do is I always like to look at the chart and draw it out so that I know exactly what calculations I need. So I'm going to do my chart, that little stepwise thing, just so I know what's going on. I know that this first line right here is talking about ice, the solid, and then we got the water, the liquid, and then we got gas right here. Okay, so using this chart will help us figure out which calculations we need to do and which numbers that we need to use. Okay, so let's start. What is our starting point in this problem?
Water.
Yeah, so we're starting with water, right? So it's going to be somewhere on this line, and it's going to be 20 degrees Celsius. Now we know that the melting point right here is 0 degrees Celsius, and we know that the boiling point right here is 100 degrees Celsius, right? So we're going to start somewhere around here. Okay, so 20 degrees Celsius. Okay, sound good? And then we're going to turn it into 150 grams or 150 degrees Celsius steam. And so I'm going to end up somewhere in the gaseous phase at 150 degrees Celsius. Okay, now this is going to tell us which calculations we need to use. First, I need to heat up the water right here. So that's going to be one calculation. The first calculation is heating up the water. The second calculation is breaking the water molecules in the heat of vaporization. And then the third calculation is going to be heating up the steam to 150 degrees Celsius. Okay, so that means we're going to have 3 separate equations, and we need to add them all up, and that will allow us to find how much energy it takes. Okay, so let's start with equation number 1. Okay, so in equation number 1, what we are doing is we're taking water, we're starting from 20 degrees Celsius, and we're taking it to 100 degrees Celsius because we need to take it to the boiling point. Okay, that's the first equation. So for this equation, super simple. We just need to use the heat formula. So Cm delta T. Okay, we're looking for heat, so we just need to plug in the values for Cm delta T. Okay, what's the specific heat of water? Yeah, it says it right here, 4.18. So we're going to plug in 4.18 joules gram Kelvin. The mass of water that we have is 14 grams. And then for our change in temperature, what's going to be our change in temperature? Yeah, 80. Since we're going from 20 to 100, our final temperature, the TF, is 100, and our TI, initial temperature, is 20. So it'll be 100 minus 20, which will be 80 degrees Celsius. So I want you guys to take a minute. You can calculate how much energy it takes to take water from 20 degrees Celsius to 100 degrees Celsius. I'll try to speed it up. Okay, so we're just going to plug and chug 4.18 times 14 times 80. And so that means in order to take the water to the boiling point, it will take 4,681.6 joules. And this is going to be the answer to the first equation. So in order to do this right here, number 1, in order to take the water from 20 degrees to 100 degrees, that's going to take 4,681.6 joules. Okay. All right, now let's do the second equation. The second equation is going to be turning the water into steam. And we call this the heat of vaporization. Now this one is really easy, okay? So the heat of vaporization, the equation right here is going to be delta H vap is equal to just the mass times, oh wait, sorry, I used the wrong value, my bad. The heat, sorry about that. The heat is equal to the mass times the delta H of vaporization, and that's written right here for you guys. So all we need to do is plug in the numbers. We still have 14 grams of water, and then we need to multiply that by 40.67 kilojoules per mole. Okay. Now, can I plug in these values exactly the way that I have them? No, why not? Yeah, it's in grams versus moles. So another thing that we have to do is we need to turn the grams into moles. So I'll do that for you guys, but just keep that in mind. You have to keep it the same unit. So 14 divided by 18 will give you, oh, lucky sevens. Okay, so 0.77. I'll keep it 7 just to keep us happy. 777 moles of water. So what we're going to do is we're going to turn this into moles of water. You could round up to 8, but I'm going to keep it 7 just because I like that number. Okay, so we'll keep it like that. And then from there, we can just multiply that value, 0.777 times 40.67, and that'll give us 31.6, and I'll keep it 0.1. Okay, but remember, this is kilojoules. Okay, keep that in mind. This is joules, and this is kilojoules. So that's going to make a difference too later in our calculations. I know these problems can get really long. That's why I didn't do a 5-step first, because a 5-step is going to be 5 different calculations and we need to add it all up. Okay, and then last but not least, we're going to do our third calculation. For our third calculation, we're going to take our gas, our steam, from 100 degrees Celsius, which is the boiling point. We're going to take it to 150 degrees Celsius. Now, this one is the same thing as the specific heat equation. We're going to do Q, C, M, delta T. I'm going to plug in our numbers. The specific heat of water vapor is 1.996 joules gram Kelvin. We're going to multiply that. It's still 14 grams. And then we need to multiply that by the change in temperature. So if we're going from 100 to 150, it'll be 50 degrees Celsius. And then from there, we can just calculate that out. 1.996 times 14 times 50. That'll give us 1397.2. That's going to be in joules. So step 3 right here is going to be 1397.2 joules. All right, almost done. Okay, but before we finish up, do you guys have any questions on that part? It's the same thing as water. We're just using the specific heat for water vapor. Okay, so let's take a vote. Who wants to calculate in joules? Who wants to do kilojoules? Okay, let's do kilojoules. I like kilojoules better too. So we're gonna turn these all into kilojoules, move the decimal 3 times to the left. That'll be 4.6816 kilojoules. 3 times to the left, that's going to equal 1.3972 kilojoules. If you keep it in joules, you'll get the same answer, just in joules, okay? And then we're going to add it all up. So 4.6816 plus 31.601 plus 1.3972. And for a final answer, we will get 37. I'll round it up to 68 kilojoules. Okay, so it's going to take 37.68 kilojoules to take 14 grams of water at 20 degrees Celsius and turn it into 150 grams or 150 degrees of steam. Okay. All righty, any questions? I know that was a lot of math. We will have some time to review this and practice it before the exam, but make sure you guys let me know if you have any questions, but that's unit 6, okay? So before we go though, let me just ask you one question. Which part of this process requires the most energy? Is it heating the water, heating the steam, or boiling it? Yeah, step 2, which is vaporizing it. And so vaporizing water takes a lot more energy than heating up water or heating up steam. That's why when you guys notice when you boil water, it takes forever to get it to start boiling, right? But once it starts, it just goes right away. And it's because it just takes so much energy to break those molecules apart. All right. Anyways, I've recorded this. If you guys missed anything, I know there's a lot of info. If you need to review it, You guys can check it out on Canvas, but other than that, congrats on finishing Unit 6, everybody.